Our Milky Way does not drift through space as an isolated island of stars. Instead, it is surrounded by a vast entourage of much smaller companions. Compared to giants like the Milky Way or Andromeda, these satellites seem insignificant, yet without them, the universe would look entirely different. As we speak, some are being physically torn apart, leaving long rivers of stars across the sky, while others may serve as time capsules from the cosmic dawn, containing secrets of how the very first galaxies formed. To study them is to peel back the layers of our own galactic history and glimpse the future of the Milky Way. When we look at the night sky through a telescope, we see a collection of countless stars, some spanning hundreds of thousands of light years while others are much smaller and fainter. This story is a long one, so let us settle in, and before we begin, do not forget to like and share. To the human eye, these objects may all appear as points of light clustered in the darkness, but for astronomers, a fundamental question remains: what actually qualifies as a galaxy? At first, it seems simple. A galaxy is a large collection of stars. But as you look closer, the line between a galaxy and a star cluster becomes difficult to draw. The deeper astronomers peer into the cosmos, the more blurred this boundary becomes. A galaxy is a system, a living environment composed of matter, gas, and invisible forces. For many scientists, one of the key features distinguishing a galaxy from a simple star cluster is gravity. In small clusters, the gravity binding the stars together comes only from the stars themselves, but in a galaxy, there is an extra element, dark matter. This mysterious substance constitutes the majority of a galaxy's mass, acting as an invisible glue. Dark matter forms a halo around a galaxy, giving it enough strength to pull in gas, shape stellar orbits, and even resist the gravitational tug of neighboring galaxies. If you were to strip away this invisible halo, the structure would quickly collapse. Therefore, many astronomers argue that a true galaxy must show signs of being supported by dark matter. Larger galaxies often pull on their smaller neighbors with powerful tidal forces. These forces stretch and distort the smaller objects until they are completely shattered. Star clusters orbiting a giant galaxy tend to be ripped apart over time, their stars scattered across the sky. However, dwarf galaxies, even extremely small ones, often remain intact for billions of years. Their dark matter halos protect them, helping them maintain their integrity even amidst massive gravitational tides. This durability is one reason astronomers treat them as true galaxies rather than mere clusters. Yet, not every system fits neatly into this rule. Some of the faintest galaxies discovered to date seem to blur this line, such as ultra-faint dwarf galaxies that contain only a few thousand stars fewer than some star clusters. However, they behave differently, they spread their stars further apart, and their movements suggest the presence of far more mass than what is visible. The only explanation is that they are dominated by dark matter. Seen this way, even systems that appear tiny and fragile can still be counted as galaxies because their invisible scaffolding is incredibly strong. Another feature used to distinguish galaxies from clusters is the ability to birth new stars. In many galaxies, gas undergoes cycles of collapse to form new generations of stars, a cycle that can last billions of years. In contrast, star clusters are usually born in a single burst. When the first stars ignite, they quickly exhaust the available gas. Without fuel, the cluster cannot create new stars. This difference in star formation history is crucial. It makes galaxies evolving ecosystems, whereas clusters are more like fossils of a one-time event. If you examine the chemical composition of the stars, the contrast becomes even clearer. Galaxies show diverse chemical fingerprints because stars are formed from gas enriched by previous generations. In comparison, the record within a star cluster is much simpler, locked in at the moment of birth. Nevertheless, even here, the edges blur. Some large star clusters, like Omega Centauri in the Milky Way, exhibit galaxy-like chemical complexity. In fact, some scientists believe Omega Centauri may actually be the remnant of a dwarf galaxy that had most of its stars and gas stripped away long ago. This possibility illustrates how tricky these boundaries are. Objects can change over time, moving from one category to another. A galaxy torn apart by tidal forces may leave behind something resembling a cluster, while a cluster with unexpected mass might secretly be the surviving core of a destroyed galaxy. Within a system, the motion of stars tells you what kind of gravity holds it together. In a cluster, stellar motion can be explained by visible mass alone, but in a galaxy, stars move too fast for visible matter to hold them back. Something else dark matter must be adding weight. By studying these movements, astronomers can determine whether a faint target in the sky is a true galaxy or just a cluster. Even with all these criteria, debate persists. If we draw the line too broadly, we might obscure the unique processes that set galaxies apart from clusters. The faintest galaxies ever found, ghosts that almost blend into the darkness, are pushing these definitions to the limit. Are these ghostly systems truly galaxies, or something in between? The answer is still unfolding. This uncertainty reflects a larger truth in science: the universe does not always fit neatly into the boxes we create. Our definitions are tools for understanding, but the universe constantly challenges them. This challenge is particularly sharp regarding galaxies, as these systems are the core of cosmic structure, homes to stars, planets, and perhaps life itself. Understanding where a galaxy begins and ends helps us understand how the universe itself is organized. If grand spiral and giant elliptical galaxies are the lords of the cosmic stage, then dwarf galaxies are their quiet companions. They lack elegant spiral arms or dazzling bright cores, but they are everywhere. In fact, when astronomers count the number of galaxies in the universe, the majority are dwarf galaxies. They are the lightweights of the galactic family, small in size and low in brightness, sometimes to the point of being nearly invisible in the dark. Our Milky Way contains roughly 200 to 400 billion stars. In contrast, a dwarf galaxy might have only a few billion, or even fewer. In the smallest examples, some contain only a few thousand stars. For comparison, a large star cluster within the Milky Way can contain hundreds of thousands of stars. A typical dwarf galaxy spans a few thousand light-years, while the Milky Way is about 100,000 light-years across. Some are compact enough to fit easily inside a single spiral arm of a large galaxy, while others are elongated and spread out, with stars sparsely distributed through space. Despite these differences, they share a common trait: dwarf galaxies lack the spectacle of large, well-ordered structures. They do not have the neatly wound arms of Andromeda or the smooth, full stellar spheres of giant ellipticals. Instead, they often appear irregular, skewed, messy, and unevenly distributed, with jagged and broken gas clouds as if they were never finished. This irregularity stems partly from their weakness: because dwarf galaxies have less mass, their gravity is not strong enough to hold onto their stars firmly. A single close encounter with a larger galaxy can distort their gas and dust, leaving behind a deformed appearance. Many dwarf galaxies are satellites of larger ones, and their appearances clearly show the scars left by these interactions. Even so, dwarf galaxies are not just scraps or debris. They are considered some of the universe's earliest building blocks. In the early universe, before giant galaxies formed, small clumps of gas and dark matter existed. It is said that over time, many of these dwarf galaxies merged with one another to build larger galaxies. In this way, the grand spirals and ellipticals we see today are the products of countless smaller systems merging over billions of years. Some dwarf galaxies survived this violent process and now orbit their larger relatives as satellites. These survivors may carry precious clues about the state of galaxies in the earliest eras. Not all dwarf galaxies look the same. Astronomers categorize them by their shape and behavior. Some are called dwarf spheroidal galaxies, sparse, dim, and often containing very few stars across a large volume. They contain almost no gas and show virtually no star formation, making them appear ghost-like and faint. Others, known as dwarf irregulars, are more active. These are clumpy, gas-rich systems that are still birthing new stars. In fact, dwarf irregulars can be quite bright in certain regions where glowing clouds of hot gas are lit up by young star clusters. Then there are dwarf elliptical galaxies, which are smoother and rounder than irregulars but smaller than the giant ellipticals common in the universe. Compared to large galaxies, dwarf galaxies tend to be poorer in heavy elements. Stars create heavy elements through nuclear fusion and supernova explosions, but in dwarf galaxies, much of this enriched material escapes. Due to weak gravity, they cannot easily retain the matter ejected by supernovas as large galaxies do. Over time, this means their gas remains more primitive, resembling the early universe. Therefore, astronomers can study environmental conditions within them that are similar to how the Milky Way looked before it was fully developed. Despite having few stars, dwarf galaxies still seem to be dominated by dark matter. In fact, per unit of mass, their ratio of visible matter to dark matter is often lower than that of giant galaxies, which is precisely why they can survive despite being extremely dim. Studying these dark halos helps scientists understand the details of dark matter's nature. Some of the smallest dwarf galaxies are even called dark matter laboratories because they are extremely sensitive to the presence of this invisible force. The Milky Way is surrounded by dozens of dwarf galaxies, the most famous being the Large and Small Magellanic Clouds. Visible to the naked eye in the southern hemisphere, these two irregular dwarf galaxies are rich in gas and young stars, interacting with each other as well as with the Milky Way. Their distorted shapes and star-forming regions are evidence of this gravitational dance. Closer in, our galaxy also possesses a group of tiny spheroidal dwarf galaxies, some of which were only discovered through surprising talent in recent years. These faint companions are so sparse they nearly vanish into the background, yet they are legitimate galaxies. Other large galaxies have their own retinues of dwarf galaxies, many may be hovering at the edge of detectability, like faint stellar clouds visible only to the most powerful telescopes. Despite their small size, dwarf galaxies can have a massive impact. When a large galaxy consumes a dwarf galaxy, it can trigger star formation, replenish fresh gas, and alter the structure of the larger system. Our own Milky Way shows signs of past mergers with dwarf galaxies, leaving stellar tracks in its halo. Some globular clusters in the Milky Way may even be the remnants of ancient dwarf galaxies stripped down to their cores. In this sense, dwarf galaxies are both the seeds of galaxies and the fuel that continues to shape them. A mystery related to dwarf galaxies is known as the missing satellites problem. According to computer simulations of dark matter, a galaxy like the Milky Way should be surrounded by hundreds or even thousands of small dwarf galaxies. However, when astronomers look at the sky, they find far fewer. Bright large galaxies are like beacons in the dark, while dwarf galaxies are more like scattered glimmers. Their small size and low brightness make them nearly invisible in wide area surveys. Detecting them requires deep and meticulous searching, and even then, many are just faint clouds in the darkness. Astronomers have learned clever ways to find these hidden galaxies. One approach is to search near large galaxies, as dwarf galaxies often cluster as companions, much like those around our Milky Way. The large and small Magellanic Clouds are the easiest to see, but fainter satellites, such as the Draco or Ursa Minor dwarf galaxies, can only be identified through detailed surveys of stellar motion and brightness. As telescopes improve, more of these faint companions are being found, and each new discovery suggests a vast number of members still waiting to be revealed. Another method involves using wide-field digital sky surveys to map the sky in detail. In recent years, projects like the Sloan Digital Sky Survey have discovered dozens of ultra-faint dwarf galaxies by picking out clusters of faint stars moving together from massive data sets. These findings show that the universe is teeming with small galaxies. However, astronomers are certain we have only found a small fraction of them. When scientists run computer simulations of galaxy formation, they begin with the growth of dark matter halos. The gravity of dark matter pulls in gas, creating conditions for star formation. In these models, small halos form first and then merge into larger ones. This process naturally produces a large number of small galaxies, far outnumbering giant ones. This is a bottom-up picture of cosmic growth. The small come first, the large follow. Evidence from our local group supports this view. The local group includes the Milky Way, Andromeda, and a host of smaller galaxies. The numerical majority in the group is indeed dwarf galaxies. Aside from the two giant spirals, almost all other members are dwarf galaxies, some being irregulars and others spheroidals that are nearly invisible even with modern instruments. This small corner of the universe provides a snapshot of a broader truth: wherever there are galaxies, dwarf galaxies are the most numerous. A dwarf galaxy with only a few million stars emits far less light than a spiral galaxy with hundreds of billions. By the time that faint light travels millions of light years to reach us, it is almost undetectable. Our telescopes must compete not only with distance but also with the glimmer of background stars, cosmic dust, and even light pollution from Earth itself. Many dwarf galaxies blend into the cosmic background like shadows. Detecting them requires long exposures and high sensitivity instruments. Even then, astronomers can often only identify them as subtle overdensities of stars rather than clear, bright galaxies. If most galaxies are dwarf galaxies, they may hold a wealth of information on how galaxies form and evolve. Large galaxies like the Milky Way have undergone many mergers, collisions, and star formation bursts, muddling their history. Because dwarf galaxies are smaller and simpler, they often preserve a more direct ancient record. The universe is often described as a web, with galaxies strung along filaments of dark matter and separated by vast voids. If dwarf galaxies dominate in number, then these filaments are far richer than we once thought. Every faint dwarf galaxy adds weight to this cosmic scaffolding, helping us map the dark matter network that sustains everything. Observatories like the Vera C. Rubin Observatory will conduct surveys across wide areas of the sky with great depth, expecting to find hundreds of new dwarf galaxies around the Milky Way and beyond. Space telescopes, free from Earth's atmosphere, will also look deeper, detecting faint smudges of light that ground-based telescopes struggle to see. In the late 20th century, astronomers began running large-scale computer simulations to understand how galaxies form. These simulations, based on known physical laws and the assumption that dark matter makes up the bulk of the universe's mass, led to a compelling path. Galaxies like the Milky Way should not exist in isolation, they should be surrounded by hundreds or even thousands of small dark matter halos, many of which should host dwarf galaxies. In other words, our Milky Way should have a swarm of tiny companions like bees around a hive. But when astronomers observed the sky, they saw not hundreds, but only dozens of known satellite galaxies. This gap between prediction and observation is the missing satellites problem. The contradiction is striking because these simulations are very successful at recreating the large-scale structure of the universe, the cosmic web, the clustering of galaxies, and the growth of massive dark matter halos all align with observations. But on small scales, like our Milky Way, the numbers do not add up. The dark matter halos that should exist in abundance seem empty, either they exist but failed to form stars, or our understanding of dark matter itself is incomplete. Initially, some suspected the problem was simple: the satellites were there but too dim to see. As digital surveys and deeper imaging came online, more faint dwarf galaxies did appear around the Milky Way. For example, the Sloan Digital Sky Survey found many ultra-faint dwarfs in the northern sky, followed by projects like the Dark Energy Survey finding more in the south. Each discovery chips away at the severity of the problem. However, to this day, the total number of known dwarf galaxies in the Milky Way remains in the dozens, far fewer than the theoretical hundreds. If they are not all just hiding, another possibility is that the assumptions in the simulations regarding the behavior of gas and stars within small dark matter halos were too optimistic. Theoretically, every dark matter halo can collect gas and form stars, but in reality, many small halos may have failed. Intense radiation from the first generation of stars and quasars in the early universe might have blown the gas away before small halos could form stars. Later, supernova explosions within early dwarf galaxies could have driven out the remaining gas, permanently shutting down star formation. If this scenario is common enough, many dark matter halos might truly be there, yet remain invisible to telescopes without any starlight to reveal them. From this perspective, the satellite galaxies described by the Schwarzschild predictions are not actually missing, they simply never lit up. There is also another possibility: the physics of dark matter might not be what we thought. Standard cosmology views dark matter as cold dark matter, which moves much slower than the speed of light and tends to clump together easily. This cold dark matter naturally generates a vast number of small dark halos, which is the very root of the missing satellites problem. But what if dark matter behaves differently? If dark matter consisted of warm dark matter that moved faster in the early universe, it would have smoothed out structures on the smallest scales, preventing too many dwarf galaxies from forming in the first place. If dark matter particles even interact with one another, they could further dissolve the smallest halos. These alternative models remain speculative, but the missing satellites problem is a major driver for exploring them. The Milky Way's satellites are not the only testing ground. In Andromeda, the number of satellites is also lower than predicted, although it seems to have a few more companions than our own galaxy. Observations of galaxy clusters provide another test. In larger environments, small galaxies seem more abundant, yet the smallest scale dwarf galaxies remain difficult to find across all scales. This puzzle repeats itself constantly. The missing satellites problem merges two different layers of mystery. On one hand, it may relate to how galaxies form. Perhaps small dark halos fail to host star formation more frequently than we assumed. On the other hand, it might involve the nature of dark matter itself. Perhaps this invisible substance in our models possesses properties we have yet to uncover. The challenge lies in distinguishing between the two. If we can detect more ultra-faint dwarf galaxies, we can confirm that many small halos do indeed birth galaxies. If not, we may need to rethink the very essence of dark matter. In recent years, progress has been made through the meticulous mapping of the sky to find stellar streams. These streams indicate that some satellites once existed and have since vanished, meaning the current roster of the Milky Way's dwarf galaxies is not the full story. Over billions of years, many more satellites may have existed, only to be absorbed or destroyed by the host galaxy. If so, the simulations might not be entirely wrong, but even accounting for those that are too dim to find or have been destroyed, a significant gap remains between theory and observation. Some estimates suggest the Milky Way should have at least several hundred satellites. Unless our surveys are missing nearly all of them, this remains a serious tension. If our cosmic approach is correct, then those missing satellites must be there. This problem forces astronomers to test the limits of their models and turn their gaze toward the smallest scales of the universe. Whether the answer lies in yet to be seen dim galaxies, physics we don't yet understand, or a bit of both, this mystery continues to drive research forward. One of the earliest methods for finding dwarf galaxies was accidental discovery. A careful astronomer scanning photographic plates of the sky might notice a faint smudge that didn't look like a known star cluster. Early discoveries were often uncertain because the difference between a loose collection of stars and a true galaxy is hard to see at a glance. But as instruments improved and digital imaging replaced film, astronomers began designing surveys specifically targeted at these faint patches. Wide-field surveys became essential tools, allowing the entire sky to be mapped in enough detail to capture even the dimmest structures. The Sloan Digital Sky Survey was a major step, using a dedicated telescope in New Mexico to scan vast areas of the sky with high precision, producing one of the most complete maps of stars and galaxies at the time. Within this massive dataset, researchers began to notice stellar overdensities, tiny patches with slightly more stars than expected. These overdensities were often dwarf galaxies, objects once ignored in the night sky that suddenly became visible through careful statistical analysis of huge data sets. Star counting thus became one of the primary methods for discovering dwarf galaxies. Rather than looking for a glowing plate, astronomers search for regions with an unusual concentration of stars. A dwarf galaxy might only appear as a slight bump on a star count curve, but with enough data and careful analysis, these bumps become the fingerprints of hidden companions. This method is especially effective near the Milky Way. Our galaxy has hundreds of billions of stars, making the background sky crowded and noisy. But when a dwarf galaxy appears, the stars in that patch of sky often share similar properties, such as color or brightness. By filtering for stars that are older, redder, or dimmer, the typical characteristics of dwarf galaxy populations, astronomers can peel away the faint galaxy from the dazzling glare of the Milky Way. The ultra-faint dwarf galaxies discovered over the past 20 years contain so few stars that they sit right at the lower limit of what we define as a galaxy. Detecting such targets requires not just powerful telescopes, but also clever signal-to-noise separation techniques. They are so dim that if you were standing inside one, you might not even realize you were in a galaxy at all. The sparse night sky would look almost identical to what we see from Earth. To reveal these fragile systems, astronomers now rely on deep surveys with far greater sensitivity than ever before. For example, the Dark Energy Survey conducted on the 4-meter telescope in Chile has been one of the most successful projects for finding new dwarf galaxies. By taking extremely deep exposures over a large area of the southern sky, it has revealed dozens of ultra-faint dwarf galaxies orbiting the Milky Way. Modern instruments also use motion to confirm discoveries. A random patch of stars might be misidentified as a dwarf galaxy, but in a true galaxy, the stars move together because of a shared gravitational field. By measuring the tiny spectral shifts caused by stellar motion, astronomers can test whether a faint group of stars is truly a galaxy. If the stars move randomly, the group might just be a cluster. But if their movements show that hidden mass is binding them together, then the presence of dark matter reveals it to be a galaxy. The Hubble Space Telescope has been used to resolve individual stars in suspected dwarf galaxies, allowing astronomers to determine their stellar ages and confirm their identity. With its sharp vision above Earth's atmosphere, Hubble can distinguish details that ground-based telescopes often blur together. Future telescopes will further revolutionize this search, bridging space and time. Large-scale surveys will scan the sky repeatedly, providing a dynamic map that reveals not only faint galaxies but also how they change over time. The process of discovery is slow, patient, and ongoing, but with every new faint smudge, the hidden structure of the universe becomes a little clearer. Around the Milky Way, dozens of smaller companions are moving in groups. These satellites vary greatly in appearance, structure, and size, yet together they outline the diversity of the galactic family. The most prominent members are the Magellanic Clouds. The Large Magellanic Cloud is visible to the naked eye in the southern hemisphere and is bright enough to be seen directly. With about 30 billion stars, it is by far the largest of the Milky Way's satellites. Its smaller sibling, the Small Magellanic Cloud, has only a few billion stars, yet it still easily outshines almost all other dwarf galaxies in our neighborhood. Both are irregular galaxies, lacking the clear spiral arms of the Milky Way or the smooth light of giant ellipticals. They are rich in gas and are actively forming new stars, displaying glowing nebulae, where stellar nurseries thrive. These two galaxies are the heavyweights among the Milky Way's entourage, and their interactions with each other and the larger Milky Way make them some of the most studied objects in the sky. Beyond them, even smaller and more fragile systems follow, such as the dwarf spheroidal galaxies, which remained hidden for a long time. They are like ghosts, often containing only a few 100,000 stars distributed over a large volume. Unlike the Magellanic Clouds, they contain almost no gas and have virtually no new star formation. Typical examples include the Fornax, Sculptor, and Carina dwarf galaxies, each being a faint collection of ancient stars orbiting at distances of tens to hundreds of thousands of light-years from the center of the Milky Way. There are also satellites even closer to the Milky Way, crawling almost unnoticed through its halo. The Sagittarius dwarf galaxy, discovered only in the 1990s, is one such companion. It is currently being torn apart, gradually being digested as it crosses the galactic plane. Long trails of stars are left in the sky, with arching shapes marking its remains. Another low-mass companion in the direction of Canis Major is undergoing a similar process of disintegration, its stars ground into an arc-like band around the outer edge of the Milky Way. These galaxies remind us that the boundaries of a galaxy are porous. The roster of satellites extends even further, out to hundreds of thousands of light-years. Companions like Leo 1 and Leo 2 orbit at extreme distances, almost at the edge of the Milky Way's gravitational influence. Despite being so far away, they remain bound by the Milky Way's gravity, moving along slow orbits over billions of years. Each system adds a different chapter to the history of the galactic family. Some show traces of ancient star formation bursts, while others present only smooth populations of elderly stars. We can categorize these satellites not only by brightness or size but also by their groups. Gas-rich irregulars like the Magellanic Clouds are Rare but spectacular, while gas-poor spheroidal dwarfs are numerous, faint, and widespread. Ultra-faint dwarf galaxies push the definition of a galaxy to the edge, and some researchers even argue that satellites might be arranged in massive planes or streams, though whether this is reality or an illusion is still debated. While the Magellanic Clouds have billions of stars and typical spheroidal dwarfs have millions, ultra-faint dwarfs may have only a few hundred to a few thousand. Yet, across this massive range, they are all considered galaxies. By mapping the Milky Way's surroundings in such detail, astronomers build a picture that includes both the current population and hints of past interactions. Bright irregulars may be newcomers that haven't yet had their gas stripped away. Faint spheroidal dwarfs might be survivors of long-term tidal battering by the Milky Way. Ultra-faint dwarfs could be fossils of the universe's first galaxies, preserved in miniature form. Every companion provides a clue to how galaxies grow. If you could strip away the dazzling glow of the Milky Way's disk and look only at its halo, you wouldn't see something smooth or empty. It would look more like a spiderweb woven of stars, thin and brittle, yet spanning vast distances. These are the stellar streams. They are no longer whole systems but shredded remains, where stars have been pulled away and stretched into long, thin arcs. The Milky Way's halo is full of them, like a cosmic graveyard burying small companions that couldn't withstand the gravity of the central giant. Imagine a small galaxy falling into the Milky Way, its stars once moved together under their own pull. But as it orbits the larger galaxy, tidal forces begin to stretch it. Stars on the far side feel a slightly weaker pull, while those on the near side feel it stronger. Over time, the system disintegrates, and the stars peel off to form long tails. These tails follow the original orbit, wrapping around the galaxy in tracks spanning hundreds of thousands of light-years. A once cohesive whole is transformed into scattered ribbons. Unless viewed through precise observations, they are almost indistinguishable from the wider halo. The most famous is the Sagittarius stream, the remnant of the Sagittarius dwarf galaxy, which wraps almost entirely around the Milky Way. Other streams, like GD1 and Palomar 5, are equally striking but much fainter. Some were left by torn dwarf galaxies, while others originated from pulled-apart globular clusters. Every stellar stream is a fossil record written in the positions and motions of stars. By studying them, scientists can retrace the orbits of lost systems and reconstruct the history of the Milky Way's growth. Detecting them isn't easy, many are extremely faint, drowned out in a sea of background stars. But with detailed sky mapping, more streams are appearing, turning what was once invisible into measurable orbital patterns. Their shapes are not determined by visible matter alone. If the dark matter halo were smooth, these streams would be elegant and continuous. But some stellar streams appear clumpy or broken, suggesting the stars were deflected. These disturbances might reveal invisible clumps of dark matter, remnants of smaller halos that failed to form galaxies. In this sense, stellar streams act as detectors, using their distortions to map the invisible structure of the Milky Way's dark matter. Even if a dwarf galaxy is completely swallowed, its stars do not disappear. They continue to travel together, sometimes for billions of years. Over time, the stream thins and spreads out, eventually blending into the halo until it's indistinguishable. But until then, it provides a window into a violent past. Some describe the Milky Way halo as an archive, where stellar streams are the documents. Taken together, they show that the Milky Way grew in layers. Without stellar streams, this history might remain hidden. The orphan stream is a particularly moving example. As its name suggests, the parent body that birthed it has been almost entirely destroyed, leaving only this trail of stars. Astronomers use the motion of these stars to calculate the orbit of the lost system, but the original dwarf galaxy is no longer recognizable. It has been erased, leaving only a track. On the other hand, Palomar 5 still has a surviving core, a globular cluster that is constantly bleeding stars into tidal tails on either side. Observations show it is slowly dissolving and will one day disappear, leaving only its stellar stream as a memory. Some stellar streams are twisted and folded, reflecting complex histories. A system might have orbited multiple times, with each pass pulling new stars into the halo. Overlapping arcs make the structure seem chaotic, but careful study reveals the rhythm of repeated destruction. These patterns aren't just mapping past interactions, they allow astronomers to test models of galaxy formation. In a way, stellar streams are evidence of continuity. The dwarf galaxies and clusters that birthed them no longer exist in their original form, but their stars still orbit the galaxy, becoming part of a new whole. The brightness and richness of the Milky Way come partly from these absorbed companions. Without them, the Milky Way would be smaller and much less magnificent. The Large Magellanic Cloud has stars spread over a wide area, active star-forming regions, and even visible features resembling spiral arms. It looks more like a scaled-down spiral galaxy than a small satellite following along. To the naked eye in the southern hemisphere, it looks like a cloud in the sky. Known long before the telescope was invented, its brightness and structure make it one of the most striking satellites, and it has been studied extensively. Its stellar mass is estimated to be about 1/10 that of the Milky Way. By the standards of a satellite galaxy, it is a giant. It also seems to possess a massive dark matter halo, allowing it to maintain itself even as it brushes past the Milky Way. This stability has allowed it to keep an ordered structure rather than being ground into dust. Astronomers can map the patterns of its stars across the sky, clearly seeing features like spiral arms and a central stellar bar similar to those in much larger galaxies. This is one reason the Large Magellanic Cloud occupies a unique place in the galaxy family. It seems to straddle the line between a truly independent galaxy and a bound satellite. Compared to many neighboring galaxies, its star formation rate is much faster. One of the most famous star-forming regions in the sky, the Tarantula Nebula, is located within the Large Magellanic Cloud. This nebula is a massive, glowing center of gas and dust where stars are being born in bulk. The brightest and most massive stars we know are located here, their powerful radiation lighting up the entire region. Supernovas have also been observed in the Large Magellanic Cloud, their explosions lighting up its sky. In 1987, the closest supernova visible from Earth in modern times occurred in the Large Magellanic Cloud, giving astronomers an unprecedented opportunity to track the entire process of such an event in detail. That explosion, SN 1987A, is considered one of the most important astronomical events of the last century, and it happened right in this extraordinary galaxy. While many small galaxies have lost their gas, the Large Magellanic Cloud still holds a vast amount of hydrogen, providing the fuel for continuous star formation. This gas reserve comes partly from its mass and potentially from its orbit. It has only recently moved closer to the Milky Way. Some studies suggest the Large Magellanic Cloud might be making its very first close pass with the Milky Way, having not yet had time to be completely destroyed by galactic tides. If this is true, we have caught it at a special moment in its history, just as it begins to feel the grip of its larger neighbor. For years, astronomers assumed the Large Magellanic Cloud had orbited the Milky Way for billions of years, completing many laps, but more recent velocity measurements show it is moving too fast for that to be the case. Instead, it may have only recently fallen into the Milky Way's influence, perhaps even bringing its own smaller companions with it. If so, the Large Magellanic Cloud is more like an invader than a long-term partner. An independent galaxy is currently on its way to becoming a satellite. Its gravity is strong enough to tug on the Milky Way itself, changing the motion of stars in the galactic disk. Some astronomers believe the Milky Way's dark matter halo might even be distorted by the pull of the Large Magellanic Cloud. The interaction between the two also leaves a massive gas trail in the sky, the Magellanic Stream. This giant ribbon of gas spans half the sky and is material stripped from the large and small Magellanic Clouds under the influence of gravity. This massive stream may one day fall into the Milky Way, bringing new fuel for star formation to our galaxy. If the Milky Way were smaller or the Large Magellanic Cloud further away, we might categorize it entirely differently. The fact that it exists in this gray area demonstrates nature's resistance to simplified classification. Galaxies, like all celestial objects in the universe, exist on a spectrum. For humanity on Earth, the Large Magellanic Cloud is not just a scientific puzzle. Navigators and storytellers in the southern hemisphere have long woven it into their traditions. Today, we use telescopes and satellites to peer into its depths, yet it still retains that ancient sense of wonder. It is simultaneously intimate and alien. The small Magellanic Cloud is an unusual companion. It lacks the tidy spiral arms of a rotating galaxy and the smooth glow of an elliptical system. Instead, it appears messy and skewed, looking more like a scattered patch of light than a meticulously crafted system. As time passes, a clearer picture emerges. The small Magellanic Cloud has not lived its life in calm isolation, it is caught between two giants, the Large Magellanic Cloud and the Milky Way. Its peculiar appearance is the direct result of being pulled by these two forces simultaneously. Located about 200,000 light-years from Earth, it is extremely close by cosmic standards, making it one of the nearest extragalactic neighbors. It contains only a few 100 million stars, far fewer than its larger sibling. This means that even by the standards of dwarf galaxies, the small Magellanic Cloud is quite pocket-sized. Because it is so close, astronomers can observe the real-time changes in its stars, gas, and shape under the influence of external gravitational pull. It is not a neat sphere or disk, rather, it has been stretched into an irregular pattern, where dense stellar regions interleave with empty gaps. One area looks like a main body, while another appears as a detached wing, as if a piece of the galaxy were being torn away. This structure is considered the result of tidal forces. The two Magellanic Clouds are very close to each other, orbiting the Milky Way like a pair of partners. For billions of years, they may have been circling one another while slowly spiraling inward toward the Milky Way. Their mutual gravity binds them together while also pulling each other out of shape. Because the small Magellanic Cloud is lighter, the signs of distortion are most obvious. Astronomers believe that the wing-like extension of the small Magellanic Cloud originated from a close brush with the Large Magellanic Cloud, an encounter where part of its material was stripped away and dragged out. Another clue to the predicament of the small Magellanic Cloud comes from its limbs. When observing the Magellanic Clouds in the radio spectrum, a massive river of gas can be seen stretching out from them. This is the Magellanic Stream, which arcs across hundreds of thousands of light-years in the sky. It is believed to have been pulled out during repeated encounters between the Magellanic Clouds themselves and with the Milky Way. Because the small Magellanic Cloud has lower mass, it has lost more gas than the Large Magellanic Cloud, which is one reason it appears so mottled today. Tidal stretching also affects the birth of stars within the small Magellanic Cloud. Typically, star formation in a galaxy depends on the availability of cold gas clouds. In the Small Magellanic Cloud, astronomers see evidence of recent starbursts, with very young and bright star clusters existing in certain regions, indicating that gravitational stress has triggered new activity. At the same time, other regions look as if they have been drained, as if the fuel for star making has been swept away. This uneven terrain perfectly fits the portrait of a galaxy being reshaped amidst a struggle. Due to its proximity, scientists can meticulously measure its stars and gas, even using high-precision instruments to track the spatial motion of individual stars. These measurements show that the Small Magellanic Cloud is not drifting quietly and obediently around the Milky Way, it possesses a complex orbit, and its irregular shape is likely a sign of it adapting to a life under the Milky Way's pull. Astronomers debate whether the large and small Magellanic Clouds will merge with each other first, or be absorbed by the Milky Way. Regardless, its current irregular form already shows that the process of reshaping is well underway. Like its larger brother, the Small Magellanic Cloud appears to the naked eye as a hazy patch on clear nights. Sailors once used it for navigation, and in astronomical history, long before telescopes revealed its true nature, observers had already noted its strange, cloud-like appearance. The Small Magellanic Cloud is a living lesson in what happens to small systems caught between giants, transformed by inescapable forces. That concludes our sharing of knowledge for today. I wish you all beautiful dreams and a wonderful day ahead. We will see you in the next episode.